Good morning, everybody. I'm going to drop about four problems for you guys to work through. I'm going to give you, let's say, till 9:22 to work through them, and then we will talk through them together. I'm going to erase the right side and then I'll redraw it after I'm done with these ones. Okay, so starting on the left here. Should be a fairly straightforward Diels-Alder. Gonna make our 6-membered ring with a double bond. We started out with a syn or a cis double bond here, which means we're going to end up syn in our product. They both have planes of symmetry to them, so we should only get one answer. Our next one is pretty similar, except now we have a bridgehead. So this middle part here is going to get pushed upward when this comes in. We can draw this two different ways, either in 2 dimensions or in 3 dimensions. So second ring with a double bond. Oxygen gets pushed up. Our dienophile would get pushed downward. We could either draw it like this, or in 3 dimensions, like this here. Nope, I'll take either answers for the test. So small. This is technically a endo product, which would be our major product. If we wanted to draw a minor product, it's possible that our dienophile portion here could come in the other direction. To give us our exo product, which would look like this here. Yep, the one where there's dashes in this for your dienophile portion of it will always be the endo. All right, I wrote down the other two. Okay, so our next two are going to start producing multiple answers. And generally speaking, if both have, so if you draw a line here and you draw a line here, and they're both asymmetric, you're going to end up with getting two products. So our first product is kind of the obvious one. We're going to make a 6-member double bond. There's a methyl here. These two are trans. So they're going to end up as anti to each other. Because they both don't have any symmetry to them, we have the ability to flip one of them over and get a different product. So now we'll have the methyl on the top. And the ethyl on the bottom here. All right, same thing with this one. These ones are asymmetric, which means we're gonna end up with two products, at least two major products. So let's start with the one that is just as it is drawn. So this can come in and attack. We'll make our 6-membered ring. Our dienophile is going to always end up on wedges, or sorry, dashes. So should give us this configuration. Everything that's in the middle is going to get pushed upward on the diene. So this methyl group here is going to get pushed upward. And then our dienophile, or sorry, our other half will get pushed downward. So these are both going to end up as dashes. Okay, they both don't have symmetry to them, so we could flip them over. We're essentially doing the exact same thing in terms of stereochemistry. The only difference is going to be that we're switching these two groups here. So we can draw the left portion of it exactly the same. And then we've flipped over where our methyl and ketone are. So our methyl should be on top now. Our ketone should be on bottom. Technically, these are both endo products, and you could draw exos if you wanted to, but you don't really need to for this. Okay, I'm going to talk through one or two more examples of doing this where there's resonance to try to eliminate different possibilities. And then I'm going to have you guys do an example or two. Let's see. So let's just do the simplest one first. Well, we can make it a little more complicated. Okay, so talking through this here. Technically speaking, there are 2 or 4 different products you can get out of this reaction. Our first one would be a normal major product where we would get basically just as it lines up. OMe gets pushed down because it's on the outside. This is considered an endo product. If we invert the stereochemistry on our dienophile portion, we can get an exit product. Alternatively, if we were to rotate our dienophile the other direction, so now the ketone is on bottom. We could also get an exit from that. Okay, we are going to eliminate 2 of these possibilities based on resonance. Our dienophile resonance is a little bit easier because it's usually just 1 step. So this double bond could shift up, and these electrons can get pushed upward to our oxygen. Our resonance for our dienophile, I'm going to do it in 1 step so we can push the electrons down. It's going to shift this double bond and then kick these electrons down to the bottom of our molecule. And now we have a negative charge here. So if we try to line these 2 up, it works well to generate this as is. And then if we try to do it the other way, now our charges aren't lining up. That negative is still going to want to attack the positive instead of attacking the double bond there. So this one on the left is the one that's more likely to happen. And therefore, this one here is going to be our major product, as that's how it aligns. I'm going to give you guys a second to get caught up. typically this kind of question would ask you like, what's the major product? So then you'd only really mark the endo. Okay, so as a reminder, I'm not going to go through a full example with these, but there's really two different places you can put these and it'll give you different resonant types. So if I put it here, this allows the electrons to go all the way down to this bottom position. Versus if our OME isn't at this slightly one shifted over position, these electrons can only move over to the top. So it's going to try to change how this is going to line up. So over here, your electrons ended up at the bottom of your molecule versus over here, they ended up at the top of your molecule. So the position of the OME can make a difference. Okay, I'm going to draw out two of these and give you guys about 8 minutes to try to go through. And actually, I'll draw out both of them. We'll give you guys about 4 minutes to do the first one. We'll walk through it, and then I'll give you another 4 minutes to do the next one. So we'll meet back here at 9:45 to talk through this one. If you get done with this one before then, you can start working on the next one. All right, so let's walk through this first one. We're gonna start off by just drawing them the way that drawing out all four possibilities. So we're making a six-membered ring with a double bond on each one of these. This OMe is not gonna have any stereochemistry. We can start out with that. All right, from here, let's draw in the stereochem on our diene portion of it. So the middle should get pushed upward. Nope, that's not upward. So we'll have a wedge for this methyl on the top, a wedge for the ethyl, and then a dash for the methyl that's on the outside. This is going to stay the same over here. Actually, this is going to stay the same on all of them. Our diene file is the only thing we're going to need to change. So once we have this figured out, we can start off by drawing our endo product. So our diene file should be going away. For exo, it would be going towards us. And then for our other one, we're just flipping it over. So our ketone on the bottom, going away, ketone on the bottom, going towards us. Okay. So that is our four products here. Taking a look at the resonance, our resonance for our diene file is pretty much always the same, which makes it a lot easier. We can push it upward. Get a positive charge here. Our diene is going to be a little bit different. We've got a methyl coming out the side of it. So if we shift this electrons down and make it double bond, the only thing we can do is pop these electrons to this position. Giving us negative down here at the bottom. So taking a look at this, these are already lined up, which means this one that's going to be the correct one. If you want to draw the other one, you can. In this case, the charges are not going to line up. And it's not going to lead to our major product. So our looks like our major product should be this one here, because this is the position where these end up lining up to give us our answer for this one. Any questions on this one before I let you guys do the other one? Okay, I'm going to redraw the other one, give you guys till 9:51, or sorry, 9:54, and then we will go through that example. On the exam, if it says draw the major product, that's all you need to draw. But if it has you like fill in all four, the instructions will be very clear if you need to do everything or just draw in a major product. And we'll go over that a little bit tomorrow on the practice exams or previous exams. Okay. You guys have about, let's say 55. So 9:55 to go through this one, and then we'll talk to it together. Because this one has a triple bond, there'll be no endo and exo. There's just going to be two products, and you're picking through one of them. All right, so because we have a triple bond, it's actually gonna get rid of any stereochemistry on the diene file. So when this does an attack, one of our two double bonds from the triple bond is going to come in. We're going to form this here, at which point we only have one of two possibilities, so we can make this twice. Either our ketone ends up in this top carbon or in this bottom carbon. If you wanted to draw these in 2D, it's going to get a little messy. It's kind of difficult to indicate how you make a two carbon bridgehead. Because this center here is sp2, there's not going to be any stereochemistry on that portion. All right, so taking a look at a resonance. Easy one is the dienophile. Nope, that's backwards. And then the more complicated one, well, more arrows, will be the diene over here. These are currently charge aligned, which means that this first product should be our major. All right, any questions about these? If not, we are going to let's take about a, I don't know, 7-minute break. So let's meet back here at 10:07, and then we will talk a little bit about electrocyclic rearrangements and maybe get to some synthesis problems. I think we are going to nix NMR for this exam because we just don't have enough time for it. So be back here at 10:07. All right, so we're going to talk through electron orbitals, which is a concept we haven't really been talking about much so far. If we take a diene, we have two double bonds on this. We could draw these out as orbitals also. When we think of a diene, we always think of it as having all of these being in the same plane. They all kind of have resonance between each other. You can see how this is kind of your double bonds here, but you could also technically like form bonds in this position. It all lines up well. There's actually 4 different energy levels that you can have for this diene here. So our lowest energy level is what we currently have drawn. I'm going to draw it out just as the bubble or the balloons first. We're going to fill in all 4 of them. As we go up in energy, we can generate what's called a node. So we're going to end up rotating 2 of them. We'll create one node here, and essentially that's the point where you don't have resonance through it anymore. So if we look at our bubble drawings, we no longer have that nice ability to do resonance like we do in this blue dotted path. I'm going to make just a bold line. We could easily get resonance here. Now we've got an empty orbital. So this is not going to have resonance. Because those electrons have to make like a 180-degree turn in order to get into the orbital they want to be at, which isn't possible. So we still have 2 double bonds. They just now have no resonance. As we push upward, we start breaking bonds. And we're going to start getting radicals on carbons. And then as we get all the way to our highest energy level, every carbon's getting its own radical. Generally speaking, this top portion never happens. There are a couple reactions that occur in this in between here, this point between where you're having double bonds in each position, but there's no resonance to them, and then actually putting in enough energy to break one of them. So generally speaking, if you heat a reaction, you can get it to the point where these double bonds are rotating away from each other. But if you throw in light, this is what's going to push you over the edge into that point where you're starting to get one set of radicals. There's a general pattern to it. So for your heat ones, they're going to end up as, I'm going to say 2N. N doesn't really mean anything. It's just like you're having sets of 2. And we start doing like the 6 and the 8 ones, you'll see how that works. And then for the light ones, it's going to be 1 plus 2N plus 1. And we'll go over these more in a minute. But this is your general configuration for 4 orbital systems. Well, let's take a look at a bigger one. All right, so let's do 6. If we have 3 double bonds here, I'm not going to draw through every orbital. Our lowest energy configuration is always going to be where everything's facing upward. This is our nice like resonance, normal, what we think of. Reactions here. If we add heat into the system, what we're going to end up is isolating each of these double bonds. So there's 3 double bonds, which means you're going to get 3 different pairs. Your first pair are going to be on the top. Your next pair is going to be on the bottom. Your last pair here is going to be on top. So first pair on top here. Next pair is on bottom. Last pair here would be on top. Still double bond, just no resonance in the point. If you throw heat into this, it's going to change what our pattern is going to be. So heat will push us to that one level above where we're actually breaking bonds. And it's going to look something like, we're still going to have 6 orbitals. So for this bottom one here, I said 2N because everything is in pairs of 2. 2 here, 2 here, 2 here. For this next one, the general pattern is 1 plus 2N plus 1. N doesn't really mean anything. It's just as many times as you can do pairs until you run into just a single electron by itself. So if I look at this here, we have 1 by itself. And now I'm just going to do pairs of 2 until I hit the end. So I can do a pair of 2 here, a pair of 2 here, and now there's only 1 left. So it's going to be a single electron by itself. So 1 by itself, a pair of 2, pair of 2, we're left with 1 by itself. All right, let's take a look at a big one just for fun. We'll do like a 10-membered system or a 5 double bond system. I'll give you guys a second to finish writing this. All right. I'm going to skip most of the levels. We're just going to do the heat one. So if you heat this solution, we've got 5 double bonds, which means that you should end up with 10 orbitals. Heat is going to cause us to have a pattern of 2n. So we're just putting them in pairs. So the first one by itself, first two pairs, second 2 pairs on bottom, next 2 pairs on top. Next 2 ones on bottom, last 2 ones here on top. I'm going to just draw it out in the molecule ones. So a pair on top, pair on bottom, pair on top, pair on bottom, pair on top here. With light, our pattern is going to be a single electron by itself. We're doing pairs of 2 until we can't anymore. So the next one will be on bottom, pair of 2 on top, pair of 2 on bottom, pair of 2 on top. We're left with 1 left, so that'll be on bottom here. So single electron by itself, pair of 2, pair of 2, single electron by itself. Okay, so why do we do all this? We are going to do a reaction which is called a electrocyclic ring closing. So we're going to be closing rings, and these orbital patterns are going to determine our stereochemistry for them. So let's start off by just the simplest ring closing. All right, if we have a 3 double bond system, like so, if we added either heat or light, this is going to let us close our ring. And because we have a 3 double bond system, we're going to generate a 6-membered ring. So what will happen is your electrons are going to shift up, over, and then down. Unlike the Diels-Alder, this is going to give us 2 different double bonds. So this top arrow here, when that shifted down, it gave us a double bond here. And then this one from the middle one could end up giving us a double bond in this position. If we do this with a 4 or 2 double bond system, We'll generate a 4-membered ring. Like so. We do this with 8. So 4 double bonds gives us an 8-membered ring. A little rough. Work my stop signs. So we're shifting a double bond up, down, and over here. So number of double bonds is going to equal your ring size times 2. Number of bonds times 2 equals your ring size. Yeah. Okay, let's talk about when we have substituents on here. I'm going to do these reactions with heat first. So we have 3 double bonds. We're going to make a 6-membered ring. It would look like this. There's 2 different possibilities for what we can get. We can either get this answer or where they're syn or where they're anti. This here. So when they are in light versus in heat, it's going to change which one we end up getting. So starting with light, we're going to take a look at those orbitals we talked about. So if I was to redraw this with orbitals in it, wherever I had double bonds, I'm going to fill in orbitals. And then we're going to use that same patterning we talked about. So if it is in heat, it's going to have that 2n pattern to it. So we're just doing pairs of 2. So if I start over here on the top, I would say that these are filled in as a pair. We can fill in our next pair on the bottom and our last pair here on the top. If I isolate just kind of those 2 endpoints, I'm going to redraw it. Twist it a little bit. So looking over here, this one had its orbital filled on the top here. This one here also has its orbital filled on the top. In order to make a bond, I want to twist them toward each other. So the 2 red dots are going towards each other. When I do that, it's going to shift these ones upward. Just looking at it, because I'm rotating it, it's going to pop them up. I'll do an example where it pops them down later. So it's popping them in the same direction. And this would lead to the syn product here. There's different names for how these rotate. So this one's rotating clockwise. This one's rotating anti-clockwise. So they're rotating different directions, which is referred to as disrotatory. Even though we end up as a syn product, because those two orbitals, to have them, the two red dots come together, because your end goal is this here. They rotated what's called disrotatory towards each other. Okay, let's do another example of this. Then we'll do some light ones. Okay, so we've got two double bonds, which means we're going to make a four-membered ring. We can start off by doing that. We're going to close this like so. If I break these into orbitals, we're using light, so it's going to be pairs of two. We have a pair of two here on the top, and then we'd have a pair of two on the bottom. Isolating the structure. Looking at the two endpoints. So this top one here with a methyl. In order to get these to come together, you would rotate this one counterclockwise. Did I say anti-clockwise earlier? That's weird. This one also gets rotated counterclockwise. When we do that, we're end up with the same thing. Yep, this one's going to get pushed upward when we're rotating it, and so will this. So they're both going to end up as syn. So they both should end up on wedges. Don't know why that keeps happening. Maybe I'll do an example they don't. Okay. And that would give us this product here. All right, with light, it's almost the exact same reaction. The only difference is going to be our orbitals. So taking a look at this here, we have three double bonds, which means we're going to make a six-membered ring. We're now doing this in light instead of heat. So we make a double bond here, double bond here, double bond here. This is going to be the general structure of our reaction. Now we have to look at the orbitals. Our pattern for light was 1 plus 2n plus 1. So we're going to have a single electron by itself here. A pair of two electrons on the bottom. Pair of two electrons on the top. Last one here on the bottom. redrawing this out. So on the top, which became the right here, we had an electron on the top, and then the bottom, which became the left, gives us this electron on the bottom. In order to get them to rotate towards each other, this needs to go counterclockwise. So does this. Oh, I never told you what this one's called. So when they were going opposite directions, it was disrotatory. When they go in the same direction, what's referred to as conrotatory. Con generally means with, and dis generally means against. So that helps a little bit. Okay, so when we rotate this one on the right, it's going to shift this one up. We're rotating this one counterclockwise. It'll push this one down here. If you're just looking at how your arrows are going, that one on the left here, it's rotating counterclockwise, which would make it go down. The part on the right, when it rotates, it's going to end up going up here. So they're going to end up anti to each other. Doesn't matter which one you make the wedge, which one to make the dash, because they're you have the plus minus. Okay, I'm going to give you guys 2 problems to kind of work through. We'll talk through them together, and then I might send you home with some synthesis problems that we'll do at the start of the class tomorrow. All right, I'm going to give you guys till 10:40 to work through. The first one, we'll talk through it, and then go through the next one with another 4 minutes. So Okay, so we've got 3 double bonds. Means we're going to make a 6-membered ring. Redrawing this to put our orbitals in. First pair is going to be on top. We've got light, so it's going to be a pattern of 1, pair of 2 on bottom, pair of 2 on top. Last one here on bottom. Isolate just the endpoints. The one on the top, which is now the right, is going to be on the top here. The one on the bottom, which is now the left, is on the bottom here. So we are rotating to get these towards the middle. Counterclockwise on both of them. So this would be counterrotatory because they're rotating with each other. Let's see. So on the right here, because we're rotating, this one's going to get pushed up. We're rotating clockwise, it puts this one down and this one up here. So our 2 methyl groups are both going upwards. They're both going to be wedges. That ethyl group got pushed down, making it a dash. Okay, I actually forgot our group here. I'm going to give you guys another 4 minutes to try to go through this one. This next problem here, so we'll meet back at 10:46 to talk through our last example. All right, so we've got 4 double bonds, which means we're making an 8-membered ring. We can start by doing that. Looking at our orbitals. We have heat, so it's gonna be rotating every 2. First 2 are on top. Next 2 are on bottom. Next 2 are on top. Last 2 are on bottom here. Drawing out just the endpoints. That's probably not enough carbons, but it's okay. On the right side, we've got an electron on the top, left side one on the bottom. We're going to be rotating conrotatory towards each other. Again. And then let's see, we're going to have this ethyl's going to get pushed up. This methyl's going to get pushed up. This one's going to go down. So our ethyl and methyl are both going to be the same to each other. We're going to make them both wedges. Our other ethyl is going to be A dash. All right. I am going to draw up a synthesis problem for you guys to do over tonight. And then we'll talk through it together. Which would be this here. My hint is that, I want you to use this as your only carbon source. So anything you use has to come from this here. And the hint is that you're going to need to make this as well as this here. So we'll talk about this at the beginning of the day on Tuesday. And I will see you guys then. So have a good rest of your Monday. I will see you guys in recitation either in 25 minutes or an hour and 25 minutes.